Welcome to lecture 27. In the last class, we have studied the different types of triaxial tests, which are more relevant and then reliable in the sense we look at the kind of response of the soil from a undisturbed or as close to nature as possible triaxial tests on undisturbed samples. We take the sample out of the ground from a tube, we set it up and then test it in the triaxial. The simplest is without any lateral confinement. You call it as unconfined compression test. In short, we call it as confined compression test, unconfined compression. So we are simply applying a vertical stress sigma. The lateral stress sigma 3 is 0. So when you plot the mode circle, sigma versus tau, you will simply get a circle. Here sigma 1 maximum, and so we will get undrained cohesion. The result will be undrained cohesion. We cannot interpret this beyond this value. In addition, next we go for more sophisticated one, wherein you are able to cover the sample with a perspex membrane so that we can apply sigma 3 first, then we can control the drainage conditions. In the second stage, we apply what is called as deviatoric stress, and we can get what you can call the three types of tests: drain test, 2 consolidated undrained test, third is purely undrained test. To distinguish between the three, I would like you to look at the drainage conditions in the three cases. We have in all triaxial tests two-stage loading. First we apply sigma 3 and then we apply the deviatoric sigma 1 minus sigma 3. In the drain test, you allow drainage in both cases. That is, when you apply the all-round pressure, you open the valve at the bottom so that the water can escape. And so all the time the pore pressure is 0. U is equal to 0, which means the effective stress is equal to the total stress. In the sample, all our applied stresses become stresses between the intergranular particles and there will be no pore pressure. In the second one, consolidation undrained test, in the first part you allow drainage, and in the other case you close the drainage and measure the pore pressure. So you are consolidating the sample under equal all-round pressure, but when you apply the deviatoric stress, you close the valve and then you can measure. Suppose here in the first stage you allow water, in the second stage you close and then measure the pore pressure. So then you can calculate, if you measure the pore pressure, in the first part anyway sigma 1 is equal to sigma applied sigma 1 or sigma 3. In the second stage you have sigma 1 minus pore pressure and sigma 3 minus pore pressure, so that you get sigma 3 prime and sigma 1 prime. You can get effective stresses both vertical and horizontal if you measure pore pressure. So it's always good to measure pore pressures in the second type of test. In the third, under both conditions the valve is closed, and then you expect in the first case U is equal to sigma 3 if the soil is saturated, and here you try to measure the pore pressure. Here also its valve is closed. So the sample is always in an undrained state. Now this is a sort of a quick test which is very similar to unconfined compression test, because in the first case, even though we are applying confining stress, the applied stress doesn't go to the soil particle or the soil effective granular stress. So the soil always remains in the initial state, and then if you try to plot the Morse circle, because the effective stresses are not changing, we'll again get similar to the unconfined compression test. Even though I may apply 3 different confining pressures, the strength is the same under all confining pressures, 3.1, sigma 3.2, sigma 3.3. The diameter of the Morse circle is the same in all the cases. So this result will be somewhat similar to the unconfined compression test when sigma 3 is 0. Whereas in the other 2 cases, we can get the strength of the soil with respect to effective stresses from the first drain test. So this is sigma 3.1, sigma 1.1, sigma 3.2, sigma 1.2, and sigma 3.3, sigma 1.3. As we increase the confining stress and allow drainage, always sigma prime is equal to sigma. The only problem is, because you want the soil to be consolidated, you need a lot of time for the pore pressure to get dissipated. But then the advantage is you will get the actual strength of the soil even in case of cohesive soils or fine-grained soils. Soils exhibit a frictional behavior. We can write the Mohr-Coulomb criterion as tau is equal to C plus C prime plus sigma prime tan phi prime. But in case of normally consolidated soils, say normally consolidated soil, C prime is 0. So even though it is a fine-grained silt or clay, it behaves like sand and it's a frictional material. The strength comes because of the interaction or the friction between particles. If the soil is over-consolidated, that means the initial overburden pressure is less than the maximum consolidation, past consolidation pressure, then what you will find is when you plot sigma versus tau, and please remember sigma is equal to sigma prime, that is the effective stresses are equal to the total stress, then you will find that there is a slight cohesion up to sigma dash c. This is the over consolidation range and this is the normally consolidation range. For confining stresses smaller than the maximum past pressure, the soil is over consolidated. Then you will find that there is some cohesion and the friction angle is phi 1 prime, whereas here it is phi prime. So if you want to describe an over consolidated soil for stresses less than the maximum past pressure, tau is equal to C 1 prime plus sigma 1 prime tan phi 1 prime. So here let me call this C1 prime. So it is kind of an apparent cohesion because of the over consolidation effect. This is not necessarily true cohesion, but this is apparent cohesion due to over consolidation. And the friction angle is phi prime 1. But for stresses greater than the maximum past pressure, please remember sigma dash c is called the maximum past consolidation pressure. The soil in the ground has experienced this pressure in the geologic history. Maybe the ground level was very high and due to erosion it has come now, or maybe there is an ice sheet. For whatever reason, ice has melted in the last ice age, after the ice age, and the soil became unloaded. Or if you go to Himalayas, the mountains are getting eroded, all the soil is getting washed into Ganges or Indus, and so the loading on the soil below is decreasing. Because of these, the over-consolidation effect has come in, but now you are applying a stress higher than the maximum pass pressure, then it behaves like a normally consolidated soil. Please remember, it doesn't matter even if it's over-consolidated, but the stresses we are dealing with are beyond the maximum pass pressure. Now, in the middle one, that is consolidated undrained test with pore pressure, you will get two envelopes, one with respect to effective stresses, which is same as drain test. I'm talking of now CU test. This is with respect to effective stresses, and this is with respect to total stresses. So I can say tau is equal to sigma prime tan C prime with respect to effective stresses, whereas this is equal to CCU plus sigma tan phi Cu. This is with respect to total stresses. The effective stresses means pore pressures are corrected for the soil sample. When you apply sigma 3, U is 0. So I will say sigma 3 is equal to sigma 3 prime. But when you apply now the deviatoric stress, which is sigma 1 minus sigma 3, we have pore pressure here. Let's say pore pressure at failure is UF. The pore pressure increases as you increase the load. We'll see how the pore pressures increase with time. And now I can say the total stresses are sigma 3 plus sigma 1 minus sigma 3 will give me major principal stress sigma 1, and the minor principal stress, of course, is sigma 3. But in terms of effective stresses, sigma 1 prime is equal to sigma 1 minus UF. This is the total vertical or major principal stress minus the pore pressure, and sigma 3 prime is equal to sigma 3 minus UF. Please remember, pore pressures are hydrostatic. So no matter what direction you apply the force, this pore pressure is acting in all directions. So whatever pore pressure is there, it will reduce the effective stress. So what happens now would be, if I look at the more circles, the total stress circle may be something like this, but the effective stress circle gets shifted to the left because this is the distance the circle shifts due to UF. Please remember, this is UF. Similarly, all other circles. So when I draw the total stress envelope, I get phi Cu and cohesion under consolidated undrained test. Whereas if I now look at effective stress circles, you will get a straight line, and this gives me. So what we find is phi prime from drain test is equal to phi prime from CU test. And we prefer this because to conduct a drain test, when you apply the deviatoric stress and allow drainage, I need to conduct the test for 1 to 2 days, 24 to 48 hours. Whereas when I do a CU test with pore pressure measurement, I can finish it in about 2 to 3, maximum 4 hours. So you speed it up, but you get the same result with respect to effective stresses. If for some reason the pore pressure device doesn't work, then we are in trouble and we get only the envelope with respect to total stresses. And when you talk of these stresses at failure, I would like to also add one more parameter. What will be the strength at very large strains? Most of the time when you test the soil, soils, as you know, are very plastic or ductile. They are not brittle materials like glass, concrete, etc. So if I plot the stress strain curve, what you will find is a curve of this kind. You may get failure or maximum stress maybe 2 to 5% strain. But if you keep conducting the test to about, say, strain level is 10 to 20%, that means you keep on deforming it. Like when you did the plastic limit test, you have seen that you can roll the thread to a very fine diameter. Soils can deform, particularly fine-grained soils. That's why you will see a potter takes a lump of clay and he can keep on pressing it to get any shape he wants. What he is trying to do is reach the ultimate or residual stress. So this is called the maximum, or sometimes we say the failure stress, but this is called sigma 1 minus sigma 3 residual, or sometimes called the yield, ultimate, So you find the strength at large strain is much smaller than the strength at the maximum one. This is a very interesting phenomena. So suppose you are looking at a slope in the Himalayas and you know that it is creeping, moving slowly over a period of 10, 20, 30 years. Then the deformations are so large, the strength is not governed by the maximum stress, but by the residual value. So if I now plot this particular value, I will get sigma, my tau, I will get phi residual. The strength at large strains. So what you will find is phi residual is less than the maximum strength. So we had to choose the appropriate strength corresponding to the kind of problem. If I have a building foundation and I do not want any failure here, it is under low strain, maybe of the order of 1% to 2%. Then I'll check with respect to the maximum strength available. Whereas if I'm studying a slope stability problem, a dock structure where you expect large strains, I go for residual value. So please remember that there are two strength parameters. One is the peak, you can also say sigma 1 minus sigma 3 corresponding to peak for small strains. Please remember, and for large strains you get residual value. And this is a very important property of soils. And this can be determined both from drain test and from consolidated undrained test. It is not possible to get it from undrained test because in the undrained test you only get one value. We are talking of pore pressures. So let us now look at the pore pressures that are developed while testing. Skempton, a geotechnical engineer at Imperial College London, way back in 1950s, worked on this problem, and in late 50s, early 60s, he said the increase in pore pressure is proportional to two quantities. The parameters are called A and B, are called pore pressure parameters. And you can see that if I want pore pressure under the effect of confining pressure, so the first part says delta U is equal to B times delta sigma 3. That is under all-round confining pressure. If you want to estimate how much is the pore pressure that's going to be built up, then it is equal to a parameter B times the confining pressure. If you want to estimate the pore pressure, let's say I call it 1 and 2, it is B into A into the deviatoric stress. The pore pressure due to the deviatoric stress is a product of B into A and the deviatoric stress itself. Now this parameter B is a function of degree of saturation. And if I plot B versus degree of saturation, we get a very interesting relationship. Suppose I plot degree of saturation 0 to 100%, and B, I go from 0 to 1. You can derive that B is equal to 1 for degree of saturation is equal to 100%, and B is equal to 0 for completely dry specimen. The reason being, when it's dry, there is no water, so there can be no pore pressure because of the confining stress. And when you have full degree of saturation or sample is fully saturated, then whatever stress you apply all around initially goes to the pore fluid. You remember the spring dashpot analogy in the case of consolidation of soils? We called it as a rigid cylinder. In the odometer or the consolidation test, at T is equal to 0, U is equal to the applied stress Q. Whatever load we put in, it goes into the pore fluid. It's exactly the same. The other interesting thing is, only when you reach full saturation, it becomes 100%. Even if it is 95%, degree of saturation is 95%, the B value could be maybe not 1, but 0.9, 0.85, etc. So when we do the test, we try to make sure the soil is fully saturated, because at the site or in the ground, most of the time, the groundwater table is high in case of soft soils. So if I have, this is the ground level, and the groundwater level is here, and if I take a sample here, suppose the groundwater level is at 1 meter or 2 meters from ground level, most of the samples are below that, so the degree of saturation is 100%. Soils are fully saturated. But the problem is, when you take the sample out of the ground, the water may escape. So we try to saturate it, and we do what is called as a back pressure technique, which you probably would study in a more advanced state or a course wherein we apply extra confining pressure, compress the air in the voids, and make the sample completely saturated. Otherwise, if you are able to saturate by continuous injection of water or wash it through applying continuous flow of water, what we sometimes do is, I connect a reservoir like a permeability test, allow the water to flow through the sample to get 100%. How do I check? So I'll apply delta sigma 3 is equal to 10 kPa. Then I'll measure delta U. I find out delta U by delta sigma 3. If it is equal to 1, we are good, because the sample is saturated. If it is less than 1, it means the soil is not saturated. Then I'll increase the stress, say delta sigma 3 10, then I'll add another 10, so I'll make it 20 kPa. So I keep applying pressure and make sure the air in the voids gets compressed. So once you make sure, in all saturated soil, you can take beta B is equal to 1. Please remember, this is a universal parameter. It's almost equal to 1 or close, exactly equal to 1 in saturated soils. In case of dense sands, maybe it is about 9. We ensure that the pore pressure parameter beta is equal to 1. Then, when you have applying, say, delta sigma 1 minus sigma 3, and you are measuring pore pressure at failure, then A is equal to, actually, A into B. Where is our equation? We said delta U is equal to, so A is equal to, B into A is the pore pressure divided by delta sigma 1 minus delta sigma 3, or I can say increment in the deviated stress. A is equal to, so this delta U by delta sigma 1 minus sigma 3 into B, but you just now found out that B is equal to 1 for a saturated soil. So I can get A. Why do I write this parameter F? Because I am looking at pore pressure at failure. So what it means is AF, that is the maximum possible value it can attain. How do I do that? When you apply the deviatoric stress, you are getting a stress strain curve. Here is the epsilon 1 minus sigma 1 minus sigma 3. So I am getting sigma 1 minus sigma 3 at failure or the peak stress. Simultaneously, you are measuring pore pressure with strain, and you will find it may increase, and corresponding to that strain, this is UF. Pore pressure also increases as you increase the deviatoric stress. So once you increase it, you will get pore pressure increasing and the deviatoric stress increasing. And then if I take the ratio, increase in pore pressure divided by, where is this? The maximum deviatorics, I get AF. AF is a very sensitive parameter. It's a function of OCR, the most important parameter. And what you find is, if I'm plotting OCR, starting from 1, maybe 10, 100 here, and I'm plotting at AF, say 0 to maybe somewhere is 1, it starts somewhere around 0.6 to 0.65 for a normally consolidated soil, and then it keeps decreasing, and you'll be surprised that A can be negative for a over-consolidated soil. A at failure can be less than 0 for highly over-consolidated soils. That's a very interesting phenomena, that you may apply compression load, but the pore pressure becomes negative. For a normally consolidated soil, or for OCR values of maybe 5, 10, 12, it can be positive. When you have a very large over-consolidation ratio, the soils try to increase in volume and you get a negative pore pressure. So we need to conduct the test for each of our soils. If you are dealing with all the marine clays around the coast of India, you have no problem. These are all normally consolidated. But if you are looking at the soils in the Garhwal Himalayas, Kashmir, the Himachal Pradesh area, etc., there the OCR value can be 10, 15, 20, and you may get very strange result of pore pressure parameter A being less than 1. So we need to study this phenomena. So let's now look at the stress strain behavior and the pore pressure behavior under different tests. Let me look at the stress, strain, pore pressure behavior. First, let's look at our shear box test, or we call it direct shear test, and let's only stick to granular material. That means we are looking at sands and gravel. We also do with fine-grained soil, but unfortunately drainage cannot be controlled. So there is no way whether we are determining the effective stresses or the total stress. Parameters with respect to effective stress are total stresses. So generally we prefer to test only sands or coarse grained material. Now when you do the test, if you remember, we have two boxes sliding each over each other when you apply a shear force under a given normal stress. This is shear stress, tau. So I can plot horizontal movement versus the shear stress, which is equal to shear force by area, gives me the shear stress. We get two kinds of behavior. The stress strain curve will increase gradually and reach an asymptotic value. The other extreme is that it will go pick up a maximum value, and under large strains it will trend exactly to the same level as the first curve. So here you have tau maximum, and here we have tau residual. The same thing here, tau maximum is equal to tau residual. Now what is this difference? If I have a loose sand, the gradual increase and constant asymptotic value is exhibited by loose sands. Whereas if I have dense sand, if you remember, we defined what is called as a relative density. dr is equal to, say the natural void ratio is En. We know the loosest void ratio and the minimum void ratio. If E in the initial stage or in the natural state is equal to the loosest state, E max, please, large void ratio means it's a very loose state, the relative density is 0. Whereas if you are able to compact it to the lowest void ratio, then you will get the numerator and denominator are equal and the ratio is 1 or 100%. So relative density varies from 0 to 100%. So if you are able to compact the sample to the densest state, you will get this clear peak, but under large strains it reduces to a very small value. Whereas if I have a loose sand and I try to carry a shear test, it gradually increases in strength and reaches the ultimate. So this is sometimes called the critical state. And at this state, it doesn't matter what the initial condition is. The soil can start with a very low void ratio or very high void ratio. In either case, the final state is exactly the same. Now, why does this phenomenon occur? It's very easy to visualize by a simple schematic. You try to get some simple marbles or spherical balls and try to arrange. There are two extreme possible arrangements. We also looked at it in the beginning of the course. If I put one particle over the other, then I get the maximum void ratios here. This is called the loose state. You cannot get anything looser than this, because the particle has to rest on the lower one and you get the looser state. Now you try to shear, then what is happening is these particles upper level will try to roll into the lower level. So the soil during the test is getting densified or getting compressed. So when I was plotting this graph, delta H versus tau, what it's trying to do is trying to adjust so that it will get to a state of packing which is finally equilibrium state. And if I now plot in the same plot delta vertical, you will find that there is always compression. This is positive. The volume of the sample keeps decreasing. So in my shear box, in our shear box, if I put a dial gauge and as you apply the shear, push it against each other, you will find that the sample is getting compressed. You will find volume is decreasing. But if you repeat the same test with a dense soil, how do we get a dense soil? The best way to visualize that would be, what I will do is, we'll put the particles in the valleys of the lower layer. So you first put series of spherical particles here, and then you put the next row inside the valley of each. If you now apply shear, the particles have to move, and they can move only when they climb over the lower one, which means in the final stage the particles will go higher up. So you will find that this gap between the lower layer, delta V1, delta V2 is greater than the initial state. And what you find is a very interesting phenomena. You get a volume increase in shear. No other engineering material exhibits this. So what you find is that particularly granular soils, and of course over consolidated soils too, dense soils exhibit volume increase. Please remember, you are trying to shear the sample, but the volume is increasing under shear. This phenomenon is called dilation. Anything that expands is called dilation. When you go to a eye doctor, he puts a liquid in the eye so that the iris or the eyeball, the one that light goes in, becomes larger. So that phenomena, that process is called dilation. Dense soils exhibit dilation and the volume increases. So because of that, the maximum stress is very high. Where the rate of increase is maximum, because you have a vertical stress here. Please remember, when you did the direct shear test, you have sigma vertical. If the soil sample is going up, it means you have to do some work. And because of that, the strength is very high. So what you then find out is that the phi value is a function of relative density. The looser the soil, smaller is the phi. The denser it is, the larger is the value of the friction angle. So you can in general say phi increases. Phi for granular material is a function of relative density and grading and angularity. Phi increases with relative density. Phi increases with grading. That means if I have well graded, phi is more, and if it is poorly graded, phi will be less. Similarly, phi increases with angularity. If you have more sharp edges, the interlocking is high, so you get higher friction angle. Whereas if it is a rounded particle, you will get a smaller value. So this is how we try to determine the strength of the sands, and you have all these tables available which will tell you phi for well graded, poorly graded, angular, rounded, and dense and loose state of soils.